Hello and welcome to Mathematics for Architects. Today I'm going to start by giving some information about this course, and then we will cover the first three topics. We'll talk about sets, about symbolic logic, and about numbers. I'm expecting us to have approximately 12 classes for this course. They'll be on Wednesday evenings between 6 o'clock and 8 o'clock. And the way I'm going to teach is, for the first approximately 60 minutes, I'm going to give a lecture in which I explain the material, and then in the second hour I will be available to answer your questions. If you don't have an hour's worth of questions, that's okay. We can finish early if necessary. Now, I'm saying approximately 60 minutes for the lesson, but depending on the topics I wish to cover, some weeks I might be more than 60 minutes, some weeks I might be a little bit less than 60 minutes. I'm going to try to split the topic so that each lecture is approximately 60 minutes. We can break the topics in this course up into 4 parts. The first part, the introduction, is about sets, symbolic logic, numbers, and Cartesian coordinates. Hopefully, this first section will be revision for you. Hopefully, you will have seen everything or most of the topics in this section before. Part 2 of this course is about the geometry of space. We're going to cover polar coordinates, a different way to describe the position of a point in a plane, conic sections, then we'll move to 3 dimensions. We'll talk about 3-dimensional Cartesian coordinates. We'll talk about vectors, and we'll use vectors to talk about the dot product and cross product. And then using those, we'll move on to talk about lines in space, planes in space, and projections of one object onto another object. Part 3 of this course is about finite mathematics. We're going to talk about combinatorics, which is a fancy way of saying counting. We'll talk about probability, and we will study graph theory. And then finally, we're going to study a type of mathematics called calculus. I'm expecting to spend 2 weeks talking about the introduction, 3 weeks talking about geometry, 3 weeks talking about finite mathematics, and then 4 weeks talking about calculus, which will bring us to 12 classes. There are lecture notes for this course, which you can find in Okan in the course content section. You will notice that the lectures and the lecture notes are very similar. So if you want something to follow along with the lectures, I suggest you print these out or have this available on another screen so you can follow as we go. We'll briefly talk about how we're going to assess this course, but let me give the disclaimer that this information may change depending on what the university decides. My plan is we will have homework, we're going to have 1 midterm exam, and we'll have a final exam. And my plan at this point is that the weightings will be 20%, 20%, and 60%. Unless the university says that this should change, we will use this distribution. For the homework, we're going to be using multiple choice tests on the Okan system. Starting next week, every week or almost every week, there will be a new test for you to do on that week's material. Midterm exam, which will probably be online on Okan, will likely be in either week 8 or week 9, and then after the end of term, we'll have a final exam. And for this, we're waiting on the university's decision. Maybe this will be online, maybe this will be a classroom exam. What do I expect of you? Well, If this was a classroom course, as this course used to be, you would be expected to study 1 to 2 hours outside of class for every 1 hour in class. So if this was a classroom course, I would be lecturing for 4 hours each week. That means each week you would be expected to study between 4 and 8 hours by yourself outside class. For an online course, we would still expect you to study the same amount. So you're going to be expected to study a total of between 8 and 12 hours per week for this course. That means 2 hours in class, and then for an online course, you're expected to do more reading and more independent study outside class. For your other study, a study outside class, you will be doing the homework tests every week or almost every week. Lectures will be available for you to re-watch. The lecture notes you can be reading, or you can read the slides, which I'll make available for you. There are lots of nice problems in the lecture notes which you can be working on. OLearn has a discussion board which you can be using to chat with other students to help each other or to ask questions to me. You could read textbooks about mathematics, or you might watch videos online, say on YouTube, by other teachers. And just as an example, there's a teacher who calls himself Black Pen, Red Pen, who has some nice calculus videos, which you may wish to watch. Let me recommend 2 good books for this course. These are not required purchases. You don't have to buy these, but you may find it useful to find a copy of one of these for extra details as we go through the material. Thomas's Calculus and College Mathematics for Business, Economics, Life Sciences and Social Sciences are the books that I am recommending. You will have noticed perhaps that in the bottom corner is the slide number. This will give you an idea of how far we are into a lecture. And the chapter title will be at the top corner. So if you're following along in the lecture notes, you'll be able to find where we are. If something is unclear in the lecture and you want to ask me at the end of the lecture, make a note of the slide number so we can go back and have another look. Our first topic for today is the idea of sets. What is a set? A set is just a collection of objects, which is specified in such a way that we always know if an object is in the set or not in the set. For example, the set of numbers 1, 2, 3, 4, and 5, which we might call the set A. Or the set B, which is a set containing 3 fruits, apple, banana, and cherry. Or maybe the set C is a set containing the letters N, E, I, and L. This symbol, this type, something which looks a little bit like a letter E, means it was a member of the set or is in the set. So for example, if we take the set B from the previous slide, the set containing 3 fruits, we can say that banana is in this set, but date is not in this set. Each of the objects inside a set is called an element of the set. If we have a set without any elements in it, it's called the empty set. And we have a special notation for the empty set. It's this circle with a line through it. This vertical line symbol means such that. So for example, if I had a set of all days x such that X is a weekend day, think about all of the days in the week, and then think about which of them are weekend days. We have Saturday and Sunday. Or we might be looking at all the numbers x such that x squared is equal to 4. What are the numbers which satisfy x squared equal to 4? They are the numbers -2 and 2. Final example, the set of all of the people in the world who are greater than 5 meters tall. Nobody in the world is more than 5 meters tall. This is the empty set. If every element of a set A is also in a set B, then we can say that A is a subset of B, and we write it like this. A is a subset of B. Some examples. The set containing 1, 2, and 3 is a subset of the set containing 1, 2, 3, and 4, because 1 is in the second set, 2 is in the second set, and 3 is in the second set. Every element of the left set is also in the right set, so the left set is a subset of the right set. The set containing banana is a subset of apple, banana, cherry, and the set containing Neil and Sezgin is a subset of set containing Neil and Sezgin, because Neil is in the right set and Sezgin is in the right set. As you can imagine, this bottom part of the symbol being is a subset or is equal to. If we're interested in the set of all the elements that we might be thinking about for a subject, we call this the universal set. Let's suppose U is the universal set, and let's suppose that A and B are subsets of U. We might think of this as of a picture like this. A is inside U and B is inside U. And then we might be interested in the set of all elements which are in A or in B. This is called the union of A and B. Or we might be interested in the elements which are in both A and B. This is called the intersection of A and B. For example, the union of the set containing A, B, and C and the set containing B, C, and D. We need every element on the left to be in the set on the right. We need A to be here, we need B to be here, we need C to be here, we need D, we need C, and we need D. So we must have A, B, C, and D. The intersection of these two sets, we're looking at the set of elements which are in both of them. B is in both sets, so we need B. C is in both sets, so we need C. A is not in both sets, and D is not in both sets. So we need the set containing B and C. The complement of A is all of the elements in the universal set which are not in A. For example, if U is the set containing the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, and A is the set containing the odd numbers 1, 3, 5, 7, and 9, then the complement of A must be the set containing the even numbers 2, 4, 6, 8, and 10. Hopefully that's all familiar to you. We will be using this type of notation throughout the course, in particular when we talk about probability. Our next topic is symbolic logic. Logic is about propositions or statements which are either true or false, but not both. For example, grass is green. We can ask, is this a true statement or is this a false statement? And in this case, this is a true statement. So grass is green is a proposition. The statement 2 plus 5 is equal to 5. It's okay to ask, is this true or is this false? And the answer is false. This is a proposition. My name is Neil. Is this true or is this false? For me, this is true. So this is also a proposition. Close the door. Is that true or false? We can't answer this question. We can't say it's true. We can't say it's false. That is not a proposition. Is it cold today? This is not a proposition. This is a question. 1. Is 1 true? Is 1 false? We can't answer that. 1 is not a proposition. We can combine two propositions together with an OR symbol. The symbol for OR is this type of V. For example, if P is the proposition, it is snowing today, that might be true, that might be false, so it's a proposition. And Q is the proposition, it is raining today. Then P or Q is the proposition, it is snowing or raining today. Or another example, if M is the proposition X is in the set A, and if N is the proposition X is in the set B, then M or N is the proposition X is in A union B. If you ever forget which notation to use, try to remember this rule. These two symbols are similar, except one is a U and one is a V. We can understand OR using the truth table. P can be true or false, so there's two choices for P. Q can also be true or false. There's two choices for Q. Multiply these two numbers together. There are 4 possibilities for P and Q. So we need 4 lines to our table. And the 4 possibilities are true, 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 false, false, true, and false, false. Let's look at the first line. If P is true and if Q is true, we can ask, is P or Q true? Is at least one of these propositions true? And the answer is yes. At least one of them is true, so P or Q is true. Let's look at line 2. Now we're supposing that P is true and Q is false. Is at least one of these propositions true? Yes. So P or Q is true. For the same reason, the third line, if P is false and if Q is true, at least one of our propositions is true, therefore P or Q must be true. And then finally we look at the bottom line. If P is false and Q is false, is at least one of P and Q true? No, so P or Q must be false. The symbol for AND is this upside down V. Same symbol that we used for OR, except this one is now upside down. For example, if P is the proposition I am hungry, and Q is the proposition I am sleepy, then P and Q is the proposition I am hungry and sleepy. Or another example, if M is the proposition X is in the set A and N is the proposition X is in the set B, the proposition M and N means X is in A intersection B. And as I said before, if you forget which symbol is OR and which one is AND, try to remember this rule because these two symbols are somehow similar. They are both open at the bottom. We have a truth table for AND. First line, P and Q are both true, and then the question is are P and Q both true? Yes, so true. Lines 2 and line 3 are both P and Q true? No, so P and Q must be false. And the bottom line, are both P and Q true? No, neither of them are true, so P and Q must be false. There is a symbol for not, which is this symbol. It's not quite a minus symbol because we have a little right hand vertical part. For example, if P is the proposition your teacher likes coffee, then not P is the proposition your teacher does not like coffee. Or if M is the proposition X is greater than or equal to 7, then not M must be the opposite of this. And the opposite of greater than or equal to 7 is strictly less than 7. A nice simple truth table for not P. If P is true, then not P, the opposite, must be false. If P is false, then not P must be the opposite. Not P must be true. The symbol for if and only if, which mathematicians often write as IFF out of laziness, is this double-headed double arrow. This means P and Q are the same. So, for example, if P and Q are both true, that means P and Q are the same. So, P if and only if Q is true. Likewise, if we look at the bottom, are P and Q the same? Yes, they're both false. So, P if and only if Q must be true. If P and Q are not the same, if one is true and one is false, then P if and only if Q must be false. One more symbol, which we will need a truth table for, is the symbol for implies, which is this single-headed double arrow. For example, P is the proposition I am in London, and Q is the proposition I am in the UK. We know that because London is in the UK, if I'm in London, then I'm also in the UK. So it's okay to write P implies Q. Let's go through the truth table, which this is perhaps the most difficult truth table, the one that confuses people the first time they see it. First line should be straightforward. P is true and Q is true. Then P implies Q is true. Using the example, if I'm in London and if I'm in the UK, is P implies Q correct? And the answer is yes. Second line, people are often happy with as well. If P is true and Q is false, let's use the example. Let's suppose P is true. Let's suppose that I'm in London. And let's suppose Q is false. Let's suppose I'm not in the UK. Is it possible for me to be in London but not to be in the UK? The answer is no. So P implies Q would be false. And then we come to the bottom two lines, which are the lines which often confuse people. P implies Q means if P is true, then Q must also be true. But if P is not true, then we don't care what Q is. If P is false, then Q might be true. That's okay. If P is false, then Q might be false. That would be okay. To understand this, let's look at the example again. Let's suppose that I'm not in London, but I am in the UK. Is it possible for me to be in the UK but not in London? Of course. And yes, of course, there's lots of cities in the UK. I could be in one of the other cities. So P implies Q could be true. Or what if they're both false? Let's suppose I'm not in London and I'm not in the UK. Is that possible? Yes, of course it's possible. Most of the people in the world are not in the UK and they're not in London. So it's okay for P and Q to both be true, but P implies Q to still be true. Let me make a couple of remarks. This implies symbol is only to be used between two propositions. Something students often write, which I don't like, is they write something like this. The integral between 0 and 1 of 3x squared dx is x cubed between 0 and 1. That's a proposition, that's a true proposition. And then you write that this implies 1. But as we discussed earlier, 1 is not a proposition. What the students mean when they write this is they mean equals sign here. But if you mean equals, then write equals. There's no need to write implies if you're not using propositions. And let me remark, if P and Q are propositions, then all of the ways of combining them that we've seen are also propositions. P or Q is a proposition, P and Q is a proposition, not P is a proposition, P implies Q is a proposition, and P if and only if Q is also a proposition. The converse of P implies Q is Q implies P. And there's another word that mathematicians use. The contrapositive of P implies Q is not Q implies not P. An example. Let's suppose P is the proposition, it is raining, and Q is the proposition, I get wet. Then P implies Q means if it is raining, then I get wet. The converse is if I get wet, then it is raining. And the contrapositive is if I do not get wet, then it is not raining. There are 22 identities that we can discuss about propositions, and I'll go through these. The first ones are straightforward, but as we get to the bottom of the list, I will need to give more details. First of all, P or P. Is P true or is P true? That's the same as P. If P is true, then P or P is true. If P is false, then P or P is false. Likewise, P and P is the same as P. If P is true, both sides are true. If P is false, both sides are false. It doesn't matter which order we write P and Q. P or Q is the same as Q or P. P and Q is the same as Q and P. If we have three propositions and we're using the same symbol or and, doesn't matter which order we do these in. P or Q and then or R is the same as P or open bracket Q or R, and the same for and. If we're taking not of P or Q, we can take the not inside the bracket, but we have to change or to and. Or if we take not inside the bracket of P and Q, we can put the not on P and Q, but we have to change and to or. For 9 and 10, think about, let's suppose we had three numbers. Let's suppose we had A multiplied by B plus C. Of course, we know that's A multiplied by B plus A multiplied by C. It's actually the same idea we can use for or and. P and Q or R is the same as P and Q or P and R. P or true. P might be true, P might be false, but true is always true. So P or true must always be true. Likewise, P and false. Is it possible for both P and false to be true? No, because false is always false. P and false must be false. P or false. If P is true, then at least one of P and false are true. If P is false, then false is we have false or false. So both false. So P or false must be the same as P. For the same reason, P and true must be the same as P. P or not P. If P is true, then not P is false. If P is false, then not P is true. There's always one thing on the left-hand side which is true, so the left-hand side, the whole of the left side must be true. And for the same reason, P and not P must be false, because at least one of the things on the left, one of the propositions on the left must always be false. Not P is the P, same as with numbers, minus 3, of course, is equal to 3. And this is where things get a little bit more complicated. P implies Q, in fact, is the same as not P or Q. P if and only if Q is the same as P implies Q and Q implies P. P and Q implies R is the same as P implies Q implies R. P implies Q and P implies not Q is the same as not P. And number 22, which is the contrapositive identity, P implies Q is the same as its contrapositive. These are perhaps not obvious, but we can prove these using truth tables. For example, let's suppose I want to prove that identity 18 is true. We have P and Q, so we need 4 rows to our table. And we fill this in with all of the possibilities: true, 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 false, false, true, and false, false. And then we need to fill in the rest of the table. We know that P implies Q from the previous slide is true, false, true, true. We can fill in not P. Not P is always the opposite of P. So the column for P is true, true, false, false. Not P must be the opposite, false, false, true, true. Q, I'm just repeating. For Q, I have true, false, so I just repeat this over here. And then I'm just looking at the right side of the table. Not P or Q. False or true is true. False or false is false. True or true is true. True or false is true. And then we compare the third column and the sixth column. Both of these columns go true, false, true, true. These two columns are the same, therefore they must be equal. This proves that P implies Q is always the same as not P or Q. We can do another one. Prove the final one, prove identity 22. Left part of the table is the same, so I won't dwell on that. I want a column for not Q, which needs to be the opposite of the column for Q. And I need a column for not P, which must be the opposite of column P. And then I'm just going to look at the right side of the table. Does false implies false? False implies false is true. True implies false is false. False implies true is true. And true implies true is true. And then again, we have two identical columns, true, false, true, true. So P implies Q must always be the same as not Q implies not P. Two more symbols before we leave. The symbol for all, you can perhaps remember because there's a letter A here in the word all, is this upside down capital A. And the symbol for there exists, which starts with the letter E, is this backwards capital E. The third and final topic for today is the topic of numbers. In the last few minutes of today's class, I'm going to briefly talk about number systems. What are the first numbers that children learn? The first number that children learn are the so-called counting numbers, 1, 2, 3, 4, 5, 6, etc. These are called the natural numbers. For example, we might write 2 is in the set of natural numbers. Or to say it in terms of language, 2 is a natural number. 7 is a natural number. We could write 7 is in N. A half is not a natural number. For most people in the world, and there's some disagreement about this, for most people in the world, 0 is not a natural number. There is a minority of mathematicians who think that 0 should be a natural number, but most of us agree that 0 is not a natural number. It makes more sense to start counting at 1. And negative numbers such as -5 are not natural numbers. What can we do in the natural numbers? We can do addition and we can do multiplication. What I mean is, if we take two natural numbers, let's say 2 and 7, we can add them together and we still have a natural number. Or we can multiply them together and we still have a natural number. But we can't do subtraction in the natural numbers because, for example, 2 minus 7 is not a natural number. So what do? What did humans do in our history when we realized that we wanted to do subtraction? We invented new numbers. And we invented the set of numbers called integers, or all of the natural numbers, 1, 2, 3, 4, 5, 6, etc., and 0, and all of the negative numbers, minus 1, minus 2, minus 3, minus 4, minus 5, etc. This set we call Z, using the special hollow Z. If you're wondering why is it the letter Z, because it comes from the German language. What can we do in Z? We can do addition, subtraction, and multiplication, but we can't do division. For example, 3, 4, and minus 5 are integers. We can add them together, 3 plus 4. We can subtract them, 3 minus 4, that's still an integer. Multiply them together, 3 multiplied by 4 is an integer. But if we try to divide them, 3 divided by 4, this is not an integer. So what do? What did humans do in our history? We invented new numbers. We invented numbers called rational numbers, for which we use this special hollow Q. This is the set of all of the fractions, or to be more precise, it's the set of all of the numbers a divided by b, such that, here's this vertical line symbol again, such that a and b are integers and b is not 0. We use Q for the English word quotient, which is another way of saying fraction. For example, 0 is a rational number because we could write 0 equal to 0 divided by 1. Likewise, 1 is a rational number. 3 divided by 4 is a rational number. 100 divided by 13 is a rational number. Minus 4, which we might write as 8 divided by minus 2, or many other ways, is a rational number. 0.12345 is a rational number. But some numbers, such as pi or the square root of 2, are not rational numbers. Not possible to write pi as a fraction. It's not possible to write the square root of 2 as a fraction. What can we do in Q? We can do addition, we can do subtraction, we can do multiplication, and we can do division, as long as we're divided by a number which is not 0. So you might ask, are we happy now? Do we have enough numbers to be able to do mathematics? And the answer is no. Why? Why are we not happy? The answer is, if we try to draw a picture of Q, we're going to have a picture which looks something like this. We're going to have a line with lots and lots of holes in the line. For example, the square root of 2 is not a rational number, so we would have a hole in our line at the square root of 2. Pi is not a rational number, so we would have a hole here. In fact, the set Q has infinitely many holes in it. So what do? What did humans do in our history to overcome this? We invent new numbers. The set of numbers we invent is the set of all of the numbers which we can write as a decimal. And we call this set R. This is the set of real numbers. For example, 0 we could write as 0.0. Okay. 23 divided by 99, we could write as 0.2323232323, etc., etc. 3/4, we could write as 0.75. Pi, we could write as 3.141592, etc., etc. It goes on and on and on. And so on. These are all real numbers. The real numbers are complete. This is a technical maths term, which means that if we draw a picture of the real numbers, we draw a line which doesn't have any holes in. So we can ask the question, are we happy now? Do we now have enough numbers to be able to do mathematics? And the answer is yes. With the real numbers, we can do some mathematics. And that is the end of today's lesson. This week, because it was the first week, I was a bit quicker than 60 minutes. Future weeks, I might be closer to 60 minutes. Next week, if you wish to get the lecture notes and read ahead, we will study chapters 4, 5, 6, and 7. You can ask your questions in chat if you have any. Okay, converse and contrapositive are they're not the same. Converse means we swap the positions of P and Q to get Q implies P. So instead of if it is raining, then I get wet, we swap these to get these over. So first we have if I get wet, then it is raining. Contrapositive means something different. Contrapositive means we don't just swap the positions of Q and P, but we also put not on them. So again, the first part is about getting wet, but there's not here. If I do not get wet, and then in the second part, then it is not raining. Again, the second part is about it being raining, but this time it's about not raining. As we see later on, P implies Q is the same as not Q implies not P. Using, we saw this in identity 22, I think it was. This is a useful trick that mathematicians use when we want to prove things. Sometimes we want to prove that P implies Q is true, but it's difficult. But it turns out that proving that not Q implies not P is easy. And because we know that they are the same thing, it's useful to use contrapositive.